Just some more extra physics here. We are moving forward with some more capacitors, capacitance, and now we're going to do something really particular with the capacitor. We're going to put something between its plates. Ooh, that sounds scary, huh? No, not really. All right, so what we're going to do is introduce the concept of dielectric materials and their utilization in capacitive systems in order to change the capacitance of the capacitor. So, dielectric materials are insulators that can be placed between the plates of a capacitor having an effect of increasing the capacitance. Of said capacitor. Exclamation point there. That's pretty cool, huh? All right, so what we're going to do is first say, hey, it's an insulative material. It's not a conductor. You put a conductor between the plates of the capacitor. If that conductor touches the plates, then you don't have a capacitor anymore because charge won't stay separated because it has a conductive pathway to discharge. That's not what we want. So we utilize some insulative material, we stick it in between the plates of a capacitor, and it has the effect to increase the capacitance of that capacitor relative to when there was nothing between the plates. So at this point we've assumed that there is air or really free space in between the plates of the capacitor. Air is actually a dielectric material that does have a little effect, but it's fairly minimal. So what are we going to do here? Well, let's just take a look at this. We're going to take ourselves a capacitor. We'll take a parallel plate capacitor because that's the easiest thing to look at. So consider parallel plate capacitor. With empty space. Between its plates. Which are connected to a source potential. Such that the capacitor is fully charged. Ooh. Turned out to be a longer sentence than I thought it would be. Anyways, this is what we've got going on here. Take ourselves some source potential, great. We've got ourselves a parallel plate capacitor. We'll just draw it out how we usually do. And we've got, there's the source potential, fantastic. This capacitor, we're just gonna call C, and we're gonna say it has capacitance C sub 0, and we'll also have some charge stored. C sub 0 is the capacitance with empty space between the plates. Q0 is the charge stored. Again, empty space between its plates. And delta V0 is the potential difference. Across its place. Again, this is all regarding empty space between its links. What? Between its links? Between its plates? Who said that? All right, so what do we do with this? Well, for now we can define the capacitance of this capacitor, C0, and say it is going to be equal to Q0 divided by delta V0, and yeah, delta V0 is equal to whatever the source potential is. Fantastic. Definition of the capacitance, great. So now we're going to take this capacitor that's fully charged and we're going to remove it from the system. So I'm going to take this capacitor out. Remove. And so it's no longer connected to the source potential, and now we've got this. Charged capacitor. Removed from the source potential. So I charge it up, and then I remove it. So great, right now it's just removed. It would still be defined the same exact way. So we have still that has a capacitance C0, and that is going to be because it stores a charge Q0 and has a potential difference across its plates, delta V0. But now I'm going to do something special. I'm going to take some material and I'm going to insert it in between the plates of that capacitor and see what happens. So now, insert. A dielectric between the plates. All right, here we go. You ready for this? Plate like that. Plate like that. There's our capacitor, and then we take some material and put it in between the plates. So now I'm going to take this. So I've got this material. It's touching the plates. So we'll just go ahead and say I just kind of sandwich it in between these plates. So this is a dielectric material. Something. So now what happens? That's the big question, right? Well, we said that a dielectric is going to increase the capacitance of the system. So let's think about what doesn't happen first, so we can kind of get an idea of what has to happen. All right, so what doesn't happen? Well, this capacitor is fully charged right now, right? Fully charged, it's not connected to anything else. Whatever charge is on this plate is the same charge on this plate, just opposite, right? Just putting this dielectric in between the plates change the amount of charge that's separated. The answer is definitely not. The charge has nowhere to go. The charge is on these plates. It can't move around, it can't redistribute itself. It's there, no matter what. So we have that Q is still equal to Q0. Charge separated remains unchanged. All right, but the capacitance doesn't. And we're just going to go ahead and say new capacitance is C, which has to be the charge stored, separated, divided by the potential difference across the plates. Well, as we just said, the charge remains the same. That's not being redistributed. So this new capacitance has to be equal to Q0 divided by some delta V. All right, that's great. Well, we know C is going to be greater than C0. Increase in capacitance occurs. So what does that really mean then in terms of before? Well, before we had C0 was equal to Q0 divided by delta V0. Now we've got C, the new capacitance, is equal to Q0 divided by delta V. Well, if we get a new capacitance but we keep the charge the same, that means that the potential difference has to change, right? And if C is greater than C0, we have to have the delta V is less than delta V0. Delta V is less than delta V0 if C is greater than C0. So it turns out that these potential differences are proportional to one another. And the proportionality really depends on the material that we're putting in between the plates of this capacitor. It is found that delta V is proportional to delta V0. And constant proportionality depends on the dielectric. On the dielectric. We write that delta V which way do we want to write this? We'll write that delta V is equal to delta V sub 0 divided by this little K looking thing. It's Greek letter kappa, but it looks kind of like a K. That's it. Such that, well, this is the constant proportionality, or 1 divided by that is really the constant proportionality. But that's it. That's how we get this correlation here. K is this. 1 is less than or equal to K, which is, I'm writing this wrong. K is, here we go, greater than or equal to 1. I say K kappa for a dielectric. Kappa is equal to 1 for free space, and air is approximately 1.0006, I think. We just say, hey, the dielectric constant of air is just about unity, so it's really when we're sticking other things in between the plates other than air, do we really have a kappa that's greater than 1. But that's it. We've got this going on right here. So what does this do? Well, this kappa being a number that's greater than 1 will produce a potential difference across the plates that is less than the potential difference that the source gave it to begin with when we've removed it from the source. So that's important here. This is no longer connected to a source potential that demands that the potential difference across its plates be equal to that of the source. Charge it up, that was the potential difference. Now it reduces by putting that material in between the plates. And we'll see why that is here in a little bit. But most of all, right now, we want to just get the idea here of, yeah, you decrease the potential difference, you've just increased the capacitance of the capacitor. So what can we write with this? Well, the new capacitance is C, which is going to be equal to, again, Q0 divided by delta V. Delta V is equal to delta V0 divided by K, which is then Q0 divided by delta V0. I keep saying K. Kappa gets, I don't know, difficult for me to say for some reason. Divided by kappa, the dielectric constant, which we can then write as kappa multiplied by Q0 over delta V0, which then, hey, Q0 over delta V0, that is, by definition, the original capacitance of the system when there was no dielectric between the plates. So we've got this, kappa times C0. And in the end, what we really want to see here is C is equal to kappa times C0. This is the factor by which there is an increase of the capacitance by sticking that dielectric between the plates of the capacitor that had a capacitance C0 when there was nothing between its plates. We increased it by some amount. If kappa is equal to 2, you've doubled its capacitance. Kappa generally goes anywhere from 1. There's some materials, strontium, titanate, something like that, has like a dielectric constant of 255 or something. Well, yeah, you stick that between the plates, you get a capacitance of 255 times that of the original capacitance. And there's other exotic materials that can produce different types of effects. But that's pretty neat, right? So we can drastically increase the capacitance of the capacitor by utilizing dielectrics. And there's some other things that go along with that as well. Well, when we have air or free space between the plates of the capacitor, really it's hard to get them really close together without touching, right? But what happens if we can take some really thin, very thin sliver of material, like a little sheet of paper, or even something thinner than that, sandwich the plates of the capacitor around that, or have that sandwich between the plates. You can get the plates separated by really small distances. They're not touching. There's a dielectric between their plates. You can basically get D, the distance of separation, to be really small, which overall increases the capacitance as well. So you can get smaller separation distances and larger overall capacitances due to the dielectric material, which both stand to increase the overall capacitance. So it's just really helpful for producing large capacitances in general. So that's what we've got going on with this. There's some other things that kind of fall out of this. Some of it's, well, why do we get a smaller potential difference across the plates? And what else is going on? And that's what we're going to look at here one moment. Be right back. All right, so what we want to do is just look at why this is happening here. What's really going on? So we consider, again, dielectric material. What is it composed of? Well, it's composed of protons, neutrons, and electrons, just like our everyday materials are. It just happens that there's no free electrons or conduction electrons that can swim around. That's great. So let's think of this dielectric material as composed of some polar molecules. We've got electron, proton combinations of molecules that, to some degree, are in random orientations when the dielectric gets all by itself. So lone dielectric. Has a random orientation of polar molecules. So we take some dielectric material here, And what do we have? This may not be completely random, but we've got something like, hey, we've got a plus minus like this. We've got a plus minus like this. We've got a minus, well, let's do plus minus again. Plus minus, we've got a trouble. Minus plus, minus plus, minus plus, plus minus, plus minus. Random orientation of these polar molecules here. So the point is that, yeah, we have some pluses and minuses such that the electric field is ultimately zero in there, and that's great. What happens if we go ahead and stick this between the plates of a capacitor that is charged? If we take ourselves a capacitor, it's charged, right? So charged capacitor. Stick this in between there. So I'm gonna come and go, insert. Well, before we even insert it, since this capacitor is charged, what does it have? It's got an electric field, right? So let's just say that this is the positively charged plate, and this is the negatively charged plate here. And it's going to have this electric field that goes from positive to negative. This is our E hat due to these outer plates. We stick this in between now. So now we've got this in between. What happens with these? Well, now these polar molecules are subjected to an electric field. And what do they want to do? They want to undergo polarization shifts, if possible, to some degree, such that, hey, the positive wants to shift towards the negative side here, and the negative wants to shift towards the positive side over here. So this one right here, this one's gonna bend like this. So we've got that particular molecule, let's stick with blue here, kind of goes, and now it's like this, plus minus. It's undergone some shift here. This one can straighten out a little bit more and be kind of a minus, plus. This one would undergo some sort of shift too. Plus minus. This one would undergo a shift where it's more this. Plus minus. This one's already sort of oriented pretty good here. We've got a minus plus, minus plus. This one would undergo shift, oops, that way. Plus minus, this one, plus shifts that way. Oops, plus shifts that way. I'm just trying to mess this up a little bit. This one, plus minus, this one, minus plus. So we get this polarization shift overall. And it's not that this is the only place. This is packed full of these polar molecules, right? All over the place. What does this do? This is the same sort of thing that we would have in saying, well, you know what? It's sort of like we get a minus induced surface charges on dielectric. That's ultimately what the effect is. Now what does that do? Well, that has its own electric field associated with it. The electric field, due to this polarization shift, goes from plus to minus. Plus is more heavily on this side, minus is more heavily on this side regarding the dielectric. So now we've got this electric field. We've got E hat due to the surface charge. Induced on the dielectric. What do we have now? Well, we've got this charge, this electric field due to these outer plates being charged, and we've got this electric field due to the polarization effect regarding the dielectric. There can be only one electric field, right? The overall electric field would be the vector sum of these two. So let me call this field actually E0, the electric field without the dielectric, or just really regarding the outer plates. This is the electric field that's induced, and then we'll look at the overall electric field. So let's write this. E0 is the electric field just due to outer plates of the capacitor, outer charged plates of the capacitor. E induced is the electric field due to polar shift within the dielectric, which leaves the total electric field between the plates with the dielectric as, all right, what is it going to be? It's going to be the vector sum of the individual fields, right? Correcto. So what do we notice? They're in opposite directions. The electric field due to outer plates is that way from plus to minus, and the electric field due to the surface charge densities induced regarding the dielectric is from plus to minus in the opposite direction. So when we've got this, E0, we've got this, E induced, hat, E total is going to be equal to E0 minus E induced. So that E total is less than the electric field that was there when the dielectric was not. What does that mean? Well, the potential difference between the plates squeeze that in, potential difference between the plates is related to the electric field for parallel plate capacitor. Pretty simplistically, delta V is equal to times D. So what happens? E decreases, delta V decreases. And the potential difference decreases, the capacitance must then increase. So ultimately, it's traced back to what happens with the electric field between the plates when we insert this material. We weaken the overall electric field, we then have a potential difference that's less than what it was before, and thus we have an increase in the capacitance of the system, because the capacitance is inversely proportional to the potential difference across the plates of said capacitor. So we could put all this together and note some other things regarding surface charge densities. Regarding surface charge densities. To get sigma charge per unit area, well, got the E total, again, is the electric field due to just the outer plates minus the strength of the electric field due to the induced surface charge density. The outer plates have a surface charge density, which we could call sigma 0 over epsilon 0. Epsilon 0, again, the permittivity of free space. Sigma 0 will just be surface charge density of the outer plates. And then we've got minus induced surface charge density divided by epsilon 0. And we'll just go ahead and start working on this. We've got that E0 is delta V0 divided by the distance of separation, so that's in general, right? And we note that delta V is going to be equal to delta V0 over K, so we can say that delta V0 is equal to kappa times a delta V, so that we can write that E has to be equal to the total potential difference divided by D, which can then be written as delta V0 or kappa D. We didn't really need this, it's the other way around, but that's the relation. Delta V0 over kappa D. And what does that say? That E is equal to V0 over kappa. The new electric field, or the total electric field, it says E total, is equal to the field just due to the plates divided by the dielectric constant. All right, so what can we do with that? Well, we'll go ahead and come on over here, and we can now say that E total is equal to the field divided by kappa, which has to be equal to sigma 0 divided by kappa epsilon 0, which has to then be equal to sigma 0 divided by epsilon 0 minus sigma induced divided by epsilon 0. So what we want to do with this is solve this on out for this right here. You notice that they all have a common factor of epsilon 0. And we can write this as, move this over here, that over there. Sigma induced is then equal to sigma 0 multiplied by, minus sigma 0 divided by kappa. And we can get a common denominator, make this look a little bit cleaner. Kappa over kappa there. So we can write this as kappa sigma 0 divided by kappa minus sigma 0 divided by kappa. That is equal to the induced surface charge density. And ultimately, how we want to do this, we could factor out some kappas here. And this as kappa sigma induced is equal to 1 divided by kappa times, oh my gosh. So 0 over kappa times kappa minus 1. Or sigma induced is equal to what we started off with. It's kappa minus 1 over kappa. That looks a little bit cleaner there. And again, that just depends on the outer plates. There's the induced surface charge density. It's depending on the surface charge density of the outer plates and the dielectric constant. There we go. All right, what happens if we have a dielectric constant of a 1? Free space, basically. We get that this is equal to 0, and there is no induced surface charge density. And if there's no induced surface charge density, we've got the electric field stays the same as we should have if we just don't insert anything. All right, so that's what we end up with here regarding the surface charge density. There's one other thing that goes along with some dielectrics. And there's a couple things, but I'll look at one right now. And that is what is known as dielectric strength. Dielectric strength has to do with the maximum electric field that the dielectric material can withstand before it undergoes what is known as dielectric breakdown. Doesn't mean that it gets all nervous and falls apart. What it ultimately means is that there is a point at which it becomes conductive. You can make basically anything a conductor if you expose it to a large enough electric field such that the electrons in it, they have to move through it. Boom. So for a given dielectric, there is what is known as a dielectric strength. Dielectric materials have dielectric strengths. Which give a maximum electric field strength that the dielectric can withstand before it becomes conductive. Becomes conductive, what happens then? Well, you exceed the dielectric strength, it becomes conductive, and it discharges itself. And it's basically no good anymore. That's it. So it's something that you got to be aware of when you have given capacitors, dielectrics, and such things. But yeah, there's some maximum potential difference that correlates with some maximal electric field strength that you can't exceed. If you exceed it, the dielectric within the capacitor undergoes dielectric breakdown, and well, it's not a capacitor anymore, or at least it's not charged. Exceeding the dielectric strength produces dielectric breakdown. Means the material becomes conductive. So, while you can increase the capacitance substantially with the dielectric, you also introduce the possibility of dielectric breakdown if you expose it to too high of a potential difference, or you want too high of a potential difference across its plates. And that's something you just got to be aware of. Generally, capacitors are rated with a capacitance and some sort of maximum voltage, which again correlates with dielectric breakdown. You look it up in a table, depends on the material that you're utilizing, and that's basically that. Some materials have really, really super large dielectric strengths. Some have relatively small. It just depends on the material itself. And that's it. All right, so leave it at that. And yeah, that sounds good. Take care.